So, so this is 470, right? You guys are gonna hate me within like 2 weeks of this class.
How's that different?
This class is so hard, it's ridiculous.
I bet this class is super easy, and you've just been talking it up.
You shut your mouth.
Here, I'm just gonna turn. We'll just turn to like a random page in here.
Random page at the beginning of the textbook.
Yeah, here. So it's just random.
Okay.
Random grammar stuff. Here, let's get to the Lambda Calculus.
Oh, that's a
Calculus.
Patterns of recursion. Yeah, here's Lambda stuff down here.
Oh, that was fun.
All right. So let's start off here. Syllabus. Syllabus is. Shut up! Syllabus is up on the site. It's your usual thingamabob, Madelia thingy. I'll bring it up real quick. All right, textbook for the class is this book called Essentials of Programming. This guy right here. I'm actually going to put a copy of this book here in the little library bookshelf guy deal here if you ever get desperate. There's actually two versions of this book. This is the second edition. There's also a third edition. I actually like the second edition better. You probably could find it online fairly inexpensively. I have a digital copy here that I use in class, so if you ever want to reference that, I'll take screenshots for assignments and stuff like that off of it, so you won't need it. But it's not a bad book to get. But if you find it on eBay or something like that for $5, probably worth getting. Probably the de facto programming languages book. Okay, then I have a link there for a Scheme language reference. We're going to be using a programming language in here called Scheme. It's actually a functional programming language. So if you remember back when I was first teaching you about programming languages, we said there's 3 different kinds of programming languages. We have procedural, object-oriented, and functional. We kind of glossed over functional. Well, now we're going to be using a functional in here. And what we're actually going to do is we're going to be creating our own programming language using a functional programming language. So we're going to be implementing constructs like variable environments, conditionals, recursion, object-orientedness, loops, implementing how those things actually work. So before you were driving a car, now we're building a car. That's what we're doing. Okay, so stupid objectives, blah, blah, blah. Topics, inductive sets, data abstraction, expressions, state interpreters, variables and types, modules, objects and classes. So we'll kind of learn about the implementation of strongly typed versus loosely typed languages. As usual in my classes, homework's 45% of your grade, 15% pop quizzes. We'll probably have a lot of those in here. 20% midterm, 20% final. Question for you. How many, well, first of all, what's recursion? What's the definition of recursion? Go ahead, DR.
When a function calls itself.
When a function calls itself, okay. Do you like recursion? Okay. How many of you think recursion is confusing? How many of you are lying? Okay, most of us. Recursion's tough, right, to wrap your mind around originally? Okay. Well, I have great news for you. Okay. Scheme doesn't support loops, so you have to do everything recursively.
Yes.
Okay. By the time this class is over, you will have trouble doing things iteratively. You will only think recursively. Okay, and you're going to cry yourself to sleep.
Can you hold me while I
All right, so yeah. So in any case, so something to look forward to, I guess, fairly quickly here. All right, so normal 90, 80, 70 grading scale. Like I said, pop quizzes. We'll do several pop quizzes, and out of curiosity, well, go ahead real quick.
How many pounds of bribery bacon counts for a letter grade?
Is it wrapped in cash? how many pounds of bribery bacon? Well, it depends. Is it wrapped in cash?
How much wrapping does it have to have to be wrapped?
Well,
How big
well,
do
just so you know how big the bribes are going to have to get, let's just go a little bit farther down the rabbit hole here. So recursion's kind of confusing, right, Doctor? All right, so his nickname's Doctor, by the way, just in case you guys missed that, for a very good and reason we can't talk about on recording. So in any case, so besides recursion being, kind of difficult to wrap your mind around, what's another kind of aspect, maybe even a benefit of recursion? Recursive solutions tend to be what? Short, right? Even very complex problems solved recursively tend to have very small solutions, right? That don't require tons of writing. Typically, quizzes would be something that doesn't require a lot of writing.
The quizzes.
So I can make very, very, very complex quizzes that are based on recursive answers that don't require you to write very many lines of code, so that when you don't know the answer, it's like the 3 magic lines that you left blank, which is extra embarrassing. If that makes sense. Evan.
Beyonce.
Oh, Beyonce, that's right. Man, you've lost your edge. Usually, historically, when I see you, I just think Beyonce, but not now. Well, no, I'm okay with Beyonce, actually. Okay, so go ahead.
So like scrap the bacon then in that case. And are you going to post the contract to sell your soul to Lucifer?
Now, interestingly enough, so first of all, normal grading scale, blah, blah, blah. Interesting enough, I've been teaching this class for a long time, about 17 years. At this university as well as the one I taught at before this. Many times I've had students who came out of this class saying, why did we need this, blah, 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 I hated this, blah, 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 all this crap. 2 years later, after they got a job somewhere, they come back and say, I use that stuff fairly often. So it's actually really good stuff that we're doing in here, but you will hate it at first because you're going to have to change your mindset at least a little bit. Okay? So you're going to be out of your comfort zone for at least a little bit. And by a little bit, I mean at least through midterms, probably.
So just after.
Huh?
Until at least just after the midterm.
Right. Yeah, but I do my normal thing. Like if you bomb the midterm and then you come back and do well in the final, I'll replace your midterm with your final exam grade. So you'll be okay. Well, probably not, but in theory. Okay. So questions about the class grading syllabus, steely, flippy thingamajig. All right, first homework assignment is already up, and you may actually get a second homework assignment today, depending on how far we get. But in any case, if you go to assignments over here, homework 1, you've got to go to Slack, CUWCS, slack.com. Most of you should already have an account on there. If you don't, go ahead and create an account on there. You can generate an account with your cuw.edu email address. It'll work just fine. Then go ahead and join the CSC470 group, and there's like a little thing that tells you what to post in it, like your name, where you're from, and something you did over the summer or something like that. There's nothing you have to post in on Blackboard. I'm just going to grade right off of there who posted in there. It's going to be important. We're going to have, maybe do announcements and stuff like that on 470. So anything I say on the 470 channel, I'm assuming you've all seen. So go ahead and set up your notifications, get the mobile app, make sure that channel has notifications. Maybe sometimes I'll even give you a free pitch and throw like a statement or something up there and say this will be the quiz tomorrow. Just checking to see if you're keeping up with Slack. Okay, so it might just be a keyword that you have to just write the keyword on the quiz, that kind of stuff. All right, so in any case, be prepared for that. I also encourage you, especially encourage you in here, to, for those of you who want to get together and work on group assignments and stuff like that, get a private group going on there, and so you can ask questions, post things about the homework. I'll be checking the public channel for questions regarding the homework, but I encourage you to collaborate. I'll find out on the midterm and the final whether or not you're learning the crap, but this stuff is going to be kind of difficult at first. And for a whole bunch of different reasons. So just kind of, I guess, be prepared. Okay. So questions about Slack. Oh, and in case you guys are posting something funny, the dean has access to the Slack channel. Is that going to be a problem?
How do you might want to clear it.
Too late.
Just wait.
Too late.
When I created a copy of the Patriarch.
Well, I haven't got to it yet. I'm not even laughing at that. All right. Sorry, I had to switch teams. I'm on multiple Slack things. That's a good one. You missed the quiz already.
No, there's no quiz.
Yes, there was.
Yes, there was.
How do you miss? How are you late the first day of class?
He was late yesterday.
You were late yesterday too.
Parking and finding this class was hard.
I mean, let's just be honest. The chances you passing this class are slim, anyways. Missing quizzes is the least of your worries. Okay.
Hey Nick, drop some cash.
Just find 20s laying around the room. All right. So, anyways, that's your first homework assignment. Make sure you have it done before the beginning of class on Thursday. I'll be going through and doing that. From that point forward, I will assume everybody has access to Slack, and anything I type in there will be read by all of you. Okay? So, punchline. Lectures as usual, blah, blah, blah. All right. So now we get to our interpreter. So the language we're going to be using in here is a language called Scheme, and we're going to be using this program used to be called Dr. Scheme. Okay, but it was taken down for censorship reasons. But in any case, now they called it Racket. Actually, for a while there, it was called Dr. Racket, but whatever.
With batteries included.
What?
That could be crazy.
That's the language?
What? Racket's not the language. Racket is like the IDE.
What's the for loop there? That's not that's scheme.
Yeah, they give you, Racket has a built-in language that they show for the programming languages book, the version 3 of it. We're not allowed to use that. All right, so,
Can we build our own?
huh?
Can we build our own?
Sure, you can build your own loop. You'll have to build it recursively, but that's fine. Yeah, I mean, one of the things you're going to be doing in here very often when you're doing your assignments is building a whole lot of little helper functions that do other things. So you're going to become very accustomed to doing that, as opposed to having a giant screen of stuff. Let me, let's see here. Let me open up the textbook. That's copying over.
You just download Racket then?
I didn't just download it.
Let's all download them once. Why not?
Okay, this is actually the 3rd edition of the book. This is from 2008. So not the identical edition that I'll be using, but in any case. Let's see. So we're going to start off with inductive sets of data. And really, we're not going to actually spend very much time there. I want to get into the language stuff pretty quickly. But one of the things we need to be introduced to first with Scheme is the idea of Scheme's primitive types. Pay attention, do your homework later. Because everybody's just posting on Slack every second. All right, so in languages you've learned up to this point, for instance, Java, I usually refer to Java as being a string-based language, correct? Okay, Java is a string-based language. Scheme I refer to, so Scheme, which is a superset of a language called Lisp. So for any of you who've heard of that, Scheme is a superset of Lisp. All right, that means it's Lisp plus extra crap. That's what superset means. So if you, doctor, you got that? You good? Sweet. All right, so Scheme is a functional language. We're going to say that it's list-based. Right? List-based. Now, having said that, we need to understand the primitive functions that are built into Scheme. Now, an interesting thing for us to kind of deal with here is, and it's kind of almost demoralizing for us when we find out how difficult some of this stuff is at first, is Scheme is actually a very small language. We don't have the 4,000 different things that Java has in it. We have like 7 built-in functions, and you have to solve everything in terms of those functions. Okay? And we're going to introduce 2 functions to you today that I maybe have referenced before, and you guys will have nightmares about these. Okay, so first, what's a list? So we're going to say a list-based primitive. I guess go ahead.
If Scheme has 7 functions, how many does list have?
Well, I'm guesstimating 7. It's more than 7. It's probably like 30. But, you know, it's not like a gigantic list.
Say 30, then comparative, how much is it?
Half. Something like that. All right, so a list in Scheme is a list of elements. And the syntax for list is single quote, open parenthesis, space separated elements, closing parenthesis. This is called a quoted list. And the quote is important. And the reason it's important is because Scheme is a list-based language, its functions, being a functional language, are stored inside of lists. So for instance, if I had, let's just say we had the function sine of 45, like that. Those 2 guys will have different results. This one says this is the list containing 2 elements. The first element is the word sine. The second element is the number 45. The second one will boil down to the sine lambda function applied to the parameter 45, giving you the result that is the sine function of 45. Okay? So we quote lists beforehand when we don't want to actually apply the first element, which would be the function name, to the parameters. Make sense? All right. So from our perspective for today, we're going to quote all of our lists because right now we're just representing data as collections of elements. All right. So a list is a collection of elements. Notice that I did not say like elements. So lists are not equivalent to arrays. They are similar to arrays, but arrays in Java require that all the elements be of the same type. We can sort of kind of fudge that a little bit with objects, but bottom line is an array construct is built to hold more than one element of the same type. In Scheme, the type does not matter because Scheme is a loosely typed language. Okay, so superset of Lisp. It's a functional language. It's a list-based language. It's a loosely typed language. It is a high-level language, so at least we have that going for us, right? It lacks loops. What other things do we have? Procedural, object-oriented, functional. We got the functional. Strongly typed, loosely typed. We got loosely typed. High level. What about compiled versus interpreted? What's the difference between a compiled language and an interpreted language? Go ahead.
Is the interpreted one where it does it once and then, or no, does it on the fly, and the compiled does it once?
Converts it between an interpreted language and converts it between a high level and a low level language in real time while the thing's running. Compiled language converts between, uses a compiler to convert between high level and low level prior to running it. And then it runs that low level language on the CPU. Scheme is an interpreted. language. Okay, interpreted languages, are these usually faster or slower languages? Slower languages, because we have that interpretation step that has to happen. Okay? Huh?
To start it, it would be faster.
To start it, it would be
Because then you have
faster.
to spend the whole time compiling it.
Well, but you can compile the program weeks ahead. You know, for those of you who just installed Windows 10, it's not like you got it and compiled it,
First time.
right? Well, but still, I mean, you didn't compile it. It was compiled back at the Microsoft headquarters, or probably in some Microsoft guy's basement. And like, this is the final gold build that breaks. All right, so this is kind of what Scheme is. And we use Scheme in here specifically because it's a simple language. Okay, Scheme is a simple language which then allows us to focus on language building constructs, how programming languages are put together. All right, so back to this idea of a list. A list in Scheme is a collection of elements, but since Scheme is a loosely typed language, those elements don't have types associated with them. So it's going to be important for us to create things known as predicates. Okay, and of course, Abe, you know what a predicate is.
Sure. I didn't know I needed grammar for this.
So I'm a pretty big advocate of buzzwords that mean simple things, right? Okay, so predicates are what your book will call this kind of crap. All a predicate is a function that returns a Boolean true when something meets a criteria and false otherwise. Okay, so you could have a predicate called even. Typically, naming conventions in Scheme would be that a predicate would be a function with a question mark after that. So even for would return true. Even is a function which is a predicate. Okay? So predicates, functions that return Booleans. Fair enough? All right, so whenever the question from the book references a predicate, that's what they're talking about. All right, so now let's talk about the cars and the cooters. So car. Car is the first function we're going to, well, we haven't actually looked at list as a function. So we're going to say car is the first function we have available to us. All right. Car returns the first element of a list. That's what car does. All right. And here, let me do this. 70, fall 2015.
So are lists index based or are they key value pairs?
Neither. Lists by definition are neither. We manipulate lists through cars and cooters. That's a partial truth, but based on the tools you have in your toolbox right now, you actually can only access the front element of a list. But officially in the Scheme programming language, the answer to your question is neither. Lists are traversed using cars and cooters, which is a nightmare. It's going to be awesome. All right. So we'll look up Racket here. That's 5.36. Did I just install 6 point something? What's this guy?
6.2.1.
All right. Give me a moment. I mean, the old one will work. It's not like they just introduced. Haha. So we're going to dump this guy. Move this guy. Well, and we're going to... Oh, just it doesn't want to go away anymore? Maybe I need to take it farther away. Nope.
He doesn't like you.
Okay, so it's the top one. Okay.
Change them up every time you come in.
Oh, hold on. I have to...
Oh, you just keep clicking on that.
No, I have to go to the security dealy flippy majiggy.
I just click on it like 3 times and eventually it lets me.
No, I don't think so. I think you have to always say, do that. All right, so we're going to go ahead and open up Dr. Racket. This is going to get our interpreter. And just as our starting point, so we can start messing with these things a little bit, let me flip back here again. Remember, something that I advertised to you before is that all programming languages support memory, asking questions, and repetition. Memory is accomplished in Scheme through the define function, which I'll show to you here in a second. Asking questions is done through an if statement, as well as something called a cond, which we haven't introduced yet, so don't pretend like these don't exist yet. And repetition is done through recursion. All right. Well, I'm going to go ahead and introduce define to you just so we can start seeing how Scheme works and how cars and cooters work. Okay. So let's see. Can I make this bigger? Okay, that makes it bigger down there. All right. We see that? Is that big enough?
It's never big enough.
Actually, we can do it. We'll do it down here. So I'm going to go ahead and I'm going to say define. So notice all functions start in they start inside of a list. So I'm going to define x to be the list 1, 2, 3. All right. So this is how I define a variable in Scheme. I use the define function that takes two parameters: the name of the variable and the value of the variable. Make sense? All right. Hit enter. Oh, I have to choose the programming language. Hold on. In the language menu, choose language. Oh, we don't want that.
I like the top one.
Yeah, we want teaching language.
Oh, that's teaching
Yeah,
language?
we want teaching languages. That'll be good enough for what we're going to do here. All right, so now I'll go ahead and define that. So now I have a variable called x. If I hit x, is it?
You just did teaching language.
Yeah.
Good.
Oh, what's going on? What are you complaining about?
This ain't good.
Is the teaching language the wrong language? Hold on. Let's find out if that's the wrong.
We need
Expected
We need the forward right one.
symbol. Oh,
Sorry, Katie. What do you think you need that forward?
shouldn't be this. I don't think that'll work. Oh, we have to define it up here. So, idea here is I was trying to do this interactive thing down here, which is like allows you to mess around with Scheme in real time. This is kind of like our program up here. So if I run the program, it executes everything everything that's up top here. So let me do it like that. Does it not like quote? I don't think it should be that. I hate this language. Some call expected a function after the opening parentheses. I gave you a function. Oh, hold on. This was the. I think I need to pick a. It wasn't just teaching language. You actually had to select a language from within here.
Well, it chose beginning student right away.
Right.
I don't think it matters. Oh, yep. which one did you select? Put the quote, single quote in there.
For this guy.
Yeah. Yep, that works.
Oh, so it was the language.
Yeah.
All right. So we should be able to do that down here. Define x 1, 1, 2, 3, like that. Oh, it was already previously defined. That should be fine. So I should be able to do it down here. So let's just start this over again. Because I'd rather do stuff down here right now. All right, so there, we have that. I hit X, shows us that X is a list. 1, 2, 3. Make sense? All right, so for those of you who missed what we just did, you under language, select choose language, choose teaching languages, and then choose advanced student. And that will give you access to the all the scheme stuff.
I think you should do the German one just to make it even more.
All right, so now that's how we define a variable in Scheme. Now, back to this car. So the first function, the first official function I'm introducing to you besides define, let's say, is the car function. The car function returns the first element of a list. So if I say car of x, what should it give me? A 1. So there's car of x. Okay? No problem? Everybody's good with that? Now again, I want to remind you that we're going to solve all of our problems in terms of the tools that are in our toolbox. Right now we have 2 tools in our toolbox. We have define and we have car. Okay, we also know about lists. All right, so now our next function, cdr. Cdr returns everything but the first element of a list as a list. Okay? You could also think of it as it returns the rest of the list as a list. All right, that's what cdr does. So, if I come in here, what's the cdr of x? The list 2, 3. Okay? So what if I want the 2? How do I get the 2 from x? I do the car of the cdr of x. That gives you the 2. Okay? This is also the cadr of x. So now I have another function, cadr.
Is there a cadr?
Mm-hmm. How do I get the 3?
Just keep adding onto it.
3 is the car of the cdr of the cdr of x, or the cddr of x. Oh, actually, the cadd. Whoa, hello. Type. The caddr of x. The caddr. There's the 3.
You just keep adding D's.
Yeah, I downloaded Racket, but it's not the same layout at all.
Got the same layout. What does it look like?
You have to go to Doctor. You have to go to Doctor Racket.
Yeah, you open Racket.
Yeah, it's Dr. Racket. There should be an icon somewhere.
Oh,
Oh, okay, there's 2 of them, alright.
Okay. So now these little shortcut things, the cadrs and the cdrs and the caddr, those are all just shortcut syntactic sugar, if you will. You never have to use those. You can always stream together cars and cdrs like this. So the car of the cdr of x, perfectly acceptable. Okay? The issue with that is going to be that as we write fairly complex things, you're going to get a lot of those mixed together. Go ahead.
Does it work to just keep adding D's if you have more elements in that list?
Yeah, like I did here. 2 Ds.
Okay. You have 3, you have 4. Is it unlimited amount of D's?
It actually isn't unlimited. There's like there is a limit, but it's like a large limit. So I mean, here if we do define y to be the list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just go there. Okay, so that would be, that's y, so we'll see. CA 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of y. Yeah, doesn't go that deep.
Stops at 4.
4? Okay. Yep. So.
But doesn't go that far. Over the, when you hold up the car CDR1 and how that works.
The who?
It's the one after you pulled the number 2 out of the list at the very. Yeah,
This guy?
the next one.
This guy.
Yeah, can you just go over that and how it
Okay.
works?
Well, so how it unwinds.
Yeah, how it
So
works.
x is. So let me just type in x real quick so we see what x is. This is x, right? X is the list 1, 2, 3. The cooter of x will be the list 2, 3. The cooter of that list will be the list 3. The car of that list will be 3. The cooter, the car.
Did you need the car?
Well, if I said I wanted you to get the 3,
Otherwise it'd be a list.
if I want you to get the 3 out of this list 1, 2, 3, I need the cooter of that list, which will give me the list 2, 3. Then I need the cooter of that list, which will give me the list 3. Then I need the car of that list, which will give me the actual 3. I'll extract the 3 from the list containing the 3.
So is it, if you didn't have the car, would it just return the 3 as a list of just 3?
Yeah, if I do the cooter of x, that'll be the list 3. Car gets you the first element of a list. Cooter gets you everything but the first element of a list as a list. Very simple. Don't overthink it. Okay? That's what makes this difficult. I've given you 2 functions that barely do anything. Okay? One of them extracts the very first element of the list. The other one gives you everything but the first element of the list as a list.
So why didn't you get 1 when you were doing the cooter of x and then the cooter of
Well, 1 would just be the car of x.
Okay.
Because x is the list 1, 2, 3. So the car of the list 1, 2, 3 would be the first element of the list, which is 1.
Right. Okay.
The cooter of x would just be the list 2, 3. The cooter would be the list 3.
Because it wasn't a
Then if you added the A onto that, it would just give you 3.
So you
That
can do
did-
a card with 2 D's in the cooter and you can get the same thing.
Yes.
Okay.
Yeah, if I do that of x, this is the same thing as saying take the car of the cooter of the cooter.
Okay.
All right, so these are shortcuts, but you never, ever, ever have to use those shortcuts. If you don't want to. You don't have to. Okay? So make sure you can wrap your mind around this because that's the important part. All right. So I've introduced 2 seemingly useless functions to you that you have to solve all problems in terms of. Fun? All right. So let's look at a couple of examples here. Let's get past the crap. Now, one of the things we're going to have to be dealing with, so we'll talk about inductive sets just a little bit because you have to understand the idea of recursively specified data and inductive sets in order to even read the problems that I'm going to be asking you to do for homework. All right, so the issue is that the questions are in a foreign language, and then you're asked to write a language to answer the foreign language with cars and cooters.
Okay.
Yeah,
Did you overthink that?
Huh?
Did you overthink that?
Think what? Did I overthink that? I learned this stuff when I was like 10. What's I doing? Oh, so here's the language of natural numbers, for example. The natural number n is in S, so the grammar would be S. So we have a language, okay, a language containing natural numbers. So a natural number n is in that language if n is either 0 or n minus 3 is in S. So kind of mathy type of set type stuff. Kind of makes sense? That's the. Don't worry about what that meant because this is just a generic definition of it, teaching you kind of how to read their rules. Okay, so they're saying that this variable belongs to this set if it fits one of these two rules, or both rules, because it has an or. So if the number is 0, it's a member of that set, or if the number minus 3 is a member of that set. Make sense? How could you tell me that differently? What would the human version of this be? Okay, what about 6?
So 0 and multiples.
Multiples of 3. Yep. Okay, zeros and multiples of 3. Or things that are divisible by 3. Okay? So that's what this says. So why didn't they just say that, right? All right, so this is how things are specified. This is recursively specified data. All right. Let's see. Oh, and here's an example of a predicate in S with a little question mark. Okay. Now, one of the reasons why I don't like this version of the book is they use some of the syntax like this, which uses some of the racket stuff, which I don't like, so I ignore that. Let's see. So one of the things they want you to do here is they want you to kind of get used to using the syntax. I don't like this aspect of the, I want us to just be able to understand how to read it rather than anything else. So like this thing says, define the set S to be the smallest set contained in N and satisfying the following two properties. So 0 is in the set S, and if N is in S, then N plus 3 is in S. So this is kind of another way. This is the inductive way of specifying the same thing that we specified up above. Don't worry about being able to specify stuff that way for the most part. Be able to read it. Okay, for where we're at now. We'll see plenty of examples.
So, this is a question. Can we use the first, second, last, etc., etc.?
You can only use things that I've introduced to you, as usual. Yeah. I will introduce things to you outside. You know, we'll keep building up our tool set, but when you answer questions, you're going to be answering them in terms of what I've taught you to do. You don't need first. First is car.
Yeah.
If you want to write your own function called first, which you don't know how to write a function yet, so you can't do that, I guess. But first is car. Last is going to be difficult since you don't know how to get how many elements are in a list.
Well, can't you just do? You get an error if you cutter and there's only one element in the list. Do you get an error?
Yeah, but you don't even know how to write an if statement to check to see if you got an error.
No, I know. I was just asking in general.
Yeah, you'll get an error. Yeah, you'll get an error. If you take the cooter of a one list, you'll get the empty list. Yeah. All right, so a couple other things they put in here. These are things they reference in some of their questions. List of integers. Something is a member of the list. Something is a member of the set that they've named list of integers if is either the empty list, so you can have an empty list of integers, or it's a pair, we'll talk about pair here in a second, whose car is an integer and whose cooter is a list of integers. So we have a list. The car of the list is a integer. So we'd have to test that against a predicate for testing for integers. And the cooter of the list is a list of integers, recursively specified data. A list of integers is either the empty list or it's a list whose first element is an int and the rest of the list is a list of integers. Make sense? All right. So, and here's the inference version of that. I'm not going to spend any time on that. It's stupid. That's stupid. Okay, so now we get to the part that's a little bit, I guess, better. So all that crap above was more the theoretical side of what we're looking at here, and this is something called grammars. Okay, what's a grammar? A grammar is the definition of a language. Okay, grammar is the definition of a language. So right here we have our idea of a list of an integer. So this grammar has two rules associated with it. Okay, two rules associated with it. We have a list of ints is the empty list. A list of ints is also a list whose first element is a list, and the rest of that list is a list of ints. They're actually referencing this as something called a pair. So instead of, I'm calling them lists because that's the way I want to teach everything in here in terms of lists. I don't want to muddy the waters with multiple things. Another reason why I don't like this version of the book. But you can build pairs, which is something that this dot actually gets put in there. I don't like that. I just do everything as straight lists. So I'm saying that a list of integers is either the empty list or it's a list containing an int followed by a list of ints. Okay? Then we have a couple of dealy things here, a couple of definition terms. Non-terminal symbols. These are the names of the sets being defined. So list of int. Okay, we're only defining one set. Terminal symbols. These are the characters in the external representation. So the dot, the parenthesis, the close parenthesis. Okay, those types of things. So really we have several things here. We have non-terminal, which is list of int. We have non-terminal, which is this idea of an int, which we've kind of assumed the existence of, right? At some point, it becomes a chicken or the egg type thing. We all know what integers are, but have we actually defined what an integer is? What would the grammar for an int be?
8 bytes numerical.
But give it to me in kind of this format.
We need to type out a list of every possible int, like 1, 2, 3, 4, all the way up to whatever we define the storage space for our ints to be. Or is there a mathematical difference?
Well, your first suggestion would take you a very long time, defined by infinity, right? Okay, so probably want to have some sort of way of defining 0 or more additional elements. So we see a weakness right now in how this is. But what's an integer in general? An integer is any of 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, followed by 0 or more of those 0 or more integers. Correct? That's what an integer is. Okay? We're just talking generics right now. Okay? But we're making this assumption right now as human beings that we at least have a decent idea of what an int is. Okay? Because then before that we can go down to, okay, well, what's a 0? Well, a 0 is, you have to give some sort of definition of what is that primitive type that is the 0, the literal 0. All right. So in any case, we have this idea of non-terminals and terminals. Right now, just treat those as vocabulary words, relatively unimportant for what we're going to be doing, but more, if they were asking you about non-terminals or terminals, it might be important. But for what we're solving, what we're going to kind of get into from the programming perspective, relatively unimportant. Okay, so then we have this idea of something called a production. So for instance, each of these guys, this is a production. This is a production. So this entire thing here is a grammar, and this grammar is made up of 2 productions. And this is recursively specified data. Why is it recursively specified data? As the doctor pointed out, is we have something that's defined in terms of itself. Okay, that's why it's recursively specified data. Okay, so that's what a production is. You can clean it up a little bit if you'd like to write it like that. This is the vertical bar for a or. Synonyms. Okay, these both say the same thing. Then we have something called the Kleene star. Kleene star syntax, which allows us to kind of pull off what you wanted to pull off. So this says a list of integers is a list containing 0 or more integers. That's what the star stands for, 0 or more. Okay, so this would be the Kleene star representation of the language that is list of integers. Make sense? Okay, what would the Kleene star representation of an integer then be? Take this a step farther. So if you were having to define int, now that you have the Kleene star syntax that we just talked about, all ints must start with, in order for something to be an int, it has to be something, right? What are the possible things that an int can start with? We could argue whether or not 0 is allowed as the starting value, right? So probably 1 through 9, followed by 0 or more ints, right? So it's still recursively specified. So the cleany star for that would be cleany star int would be, okay, we're going to say an int is either a, we have to define a couple of things here. Actually, to make this simple, let's assume we can start an integer off with 0, just so I don't have to go too much deeper into this. So we're going to say an int is 0, or an int is 1, or an int is 2, or an int is 3, or an int is 4, or an int is 5, or an int is 6, or an int is 7, or an int is 8, or an int is 9, or an int is an int star. So any of those things followed by 0 or more of those things. Why is this wrong? What does this allow for? Did you just make that up?
Yeah.
Look at the language. Give me an example of something that you know to not be an int that this would allow for. Specifically, the very last production. Does this allow us to have nothing? And is nothing an int? Nothing's not an int. So this isn't allowed. That would be allowed. Plus sign, 1 or more. Okay? So again, focus on this from the perspective of being able to read this instead of write it. Okay, that's the cleany plus. Cleany plus side, 1 or more. All right. That's our list of ints. Here, now we have something called an S list. So an S list is a list of symbols. So instead of it being a list of numbers, now we have a list of symbols. So it's a list followed by, so now we have 2 different productions. We have a grammar for something called an S list. We have a grammar for something called an S expression. An S list is a collection of 0 or more S expressions, a list of 0 or more S expressions, where an S expression is either a symbol or it's an S list. Ooh, wait a minute. Give me an example of some things that fit this grammar. You made at the beginning.
At the beginning class, that said list 1, 2, 3.
Okay.
List could have been a symbol. And then
Okay, well, 1, 2, and 3 are numbers, not symbols. So probably like A, B, and C.
Yeah.
So an S list, by that definition, let me just start this over so we can blank it out. So we might define X to be the list A, B, C. And that would fit the rules for an S list. So we have a list A, B, C, and I'm telling you that A is a symbol, B is a symbol, C is a symbol. So if I say symbol, question mark, car of X, we get a true. So there's another function for you. You have a predicate called symbol that will test whether a value is a symbol. Make sense? So we'll add that to our toolbox.
Can you make a number a symbol?
Sort of, kind of. There is a concatenation thing, but for right now, let's say no.
So what defines a symbol?
Toolbox. We have define, we have car, we have coder, and we have symbol. That's what we have access to right now. Okay, and here I'll give you access to number as well. So for instance, if I say number car of X, we get false because A is not a number. Make sense? All right. So getting back to what we were just kind of looking at, though, we have the list ABC here. And what we're looking at this against is whether or not the list ABC fits the definition of an S list. Okay? For starters, an S list must be a list, correct? That's what the syntax right here says. It's a list containing 0 or more S expressions. Make sense? So right off the bat, does this meet the original production's minimal requirement of being a list? The list ABC is a list, correct? So we're good there. So now we need to decide, is it a list containing 0 or more list expressions? Or S expressions, sorry, S expressions. What's an S expression? Well, it's either a symbol or it's an S list. Is the list ABC an S list? Sure. Give me another example of an S list. A more interesting S list. A more complex S list. Well, it's not really more complex. Let me ask you this. Define Y to be A, B, C. Is that an S list? What's an S list? An S list is a list of S expressions, where an S expression is either a symbol or an S list. And what's an S list? It's a list of S expressions. So what's this guy? This guy's a list whose first element is a symbol, whose second element is a list containing something whose first element is a symbol, whose second element is a list, whose first element is a symbol. So this guy is an S list, this guy is an S list, this guy is an S list, so the whole thing is an S list. Make sense? Any of you believe me yet that this is going to be a hard class? Seems like cake. All right, so let's go back here. So that would be an example of an S list. So here's some example of this thing. So here they showed lots of nesting as the thing here. Okay. I don't want to show you that down there. I want to ask you to help me write a grammar for a binary tree. All of you in here have had CSC470. What's a binary tree? This has nothing to do with a scheme or anything. Just what's a binary tree?
Self-sorting.
Day 2.
Okay, yeah, so at most 2 children. Everything to the left is less than or equal to the root node. Everything to the right is greater than the root node. Okay, so a binary tree is, what's the minimalistic binary tree? Let's create our first production. Can we have the empty tree? So are we allowed to have an empty tree? Sure. Okay, so we'll have our, here, I'm going to call it a B tree just for our sake of typing. So B tree, we're going to represent this as a list, right? Because this is a list-based language. So we're going to start off with empty list. Okay, for right now. Okay, what's a one-step more complex tree than the empty tree? One value, one node, something like that. Okay, so now we're going to have a production here called a node. Okay, and binary trees are usually collections of numbers, correct? So we got to know if something is less than or greater than something else. We can certainly do symbols too, but let's just stick with numbers for this. So a node or value, in fact, let's just use your term value, must be an int, right? So a binary tree is a int, at least one int, followed by what? Actually, let's do this as a second production. It's either the empty tree, or it's a tree containing an int followed by what? Followed by a B tree. So it's an int followed by, well, let's keep it this for right now. An int followed by a B tree. What's a B tree? A B tree could either be the empty list, or it can be an int followed by another B tree. But aren't there a left and right child to B trees? So the left child would be a B tree. What would the right child be? B tree? So B tree is either the empty list, empty tree, or it's an int followed by a left and a right B tree. Where a B tree is either the empty tree, or it's an int followed by a left and a right B tree. Does that make sense? Now when we wrote binary trees in Java, it seemed like there was a lot more to it than that. This is a pretty simple definition of a binary tree. We can go a couple different directions with it, but at least the high level, this makes sense as a binary tree.
So is this actually owning the object, or is this just a pointer to it?
Oh, this isn't even scheme. This is just a grammar. Yeah, this is just, we're still dealing with grammar stuff. This is just a formal representation of a binary tree grammar. Let's go something along those lines. There's another course that some computer science programs offer. It would be neat if we do it here, but you're kind of getting pieces of it here. It's something called Automata and Computation theory. So this stuff here is something called Automata. Way of defining grammars, defining languages, that kind of crap. Okay, so there's our symbol. So they kind of define their binary tree to be a little different, where the root node was a symbol followed by two trees instead of a number, that kind of crap, but whatever. And then they didn't have theirs list-based like we did. Okay, now we get to Lambda Calculus crap. All right, so this is actually the first language construct that we're learning in here. Okay, so we talk about initially, what is a lambda expression? So we're going to add it to our toolbox first, and then we're going to define it. All right, right off the bat, we might say that the word lambda might feel a little intimidating, right? Like it doesn't seem like this is going to have anything to do with anything easy. Do you agree with that? Okay. Anybody know what a lambda expression is? Go ahead.
You're sort of passing a function onto a variable. So you have a function, and then you're kind of applying that to a symbol or something.
Okay. So that's correct. So the probably a simplified way of saying this would be an unnamed function. That's what a lambda is. Lambda is an unnamed function. Well, think about the programming languages you've worked with before, Java, for example. When we write methods in Java, they have names, and then they have lists of parameters, and then they do something, right? So if we took the name out, what would we have? List of parameters and the do something. Okay, that's what a lambda is. Lambda is the list of parameters and the do something, everything but the name. Okay, so lambda is unnamed functions. So now we have access to those dudes. All right. Haven't written them in Scheme yet, but I've at least introduced the idea here. So now they've given us the grammar for a lambda expression, and this actually is the scheme grammar for it. Okay, this is actually a simplified version of it because, well, here, we'll let you explain it to me. If this is a lambda calculus expression, and I'm telling you scheme supports a function called lambda that allows us to emulate this, give me some examples of things that would be lambda calculus expressions. Let's start off with the simple one that matches the very first production. What do you think an identifier might be? I'm okay with that. Yeah, kind of a variable namey thing, right? Okay, a word, variable namey thing. So this is an identifier that kind of falls into the category here is like int. Is that competence or complete guess in the dark?
It says it right below the,
Oh, does it? Oh, okay. Whatever. Okay, but in any case, it's a well, so at least you can read. All right. So in any case, an identifier is kind of falls into the same categories like int or symbol, things we've seen already. So it's kind of, as it's used here, it's kind of like a variable name. All right. So for instance, a lambda calculus expression could just be a, or b, or cat. Okay, those would be lambda calculus expressions. All right, so that gets the simple production out of the way. Second production. Give me an example of something that would fit the second production.
You scroll down,
Just like before, when you gave me examples of S lists, you said, okay, an S list would be the list ABC. I think you said 1, 2, 3, but whatever, you know. Okay, so the list ABC would be an S list, right? So give me an example of a string that matches. So in this case, it would be a list that matches the second production of the lambda calculus expression grammar. Go ahead.
So you do lambda and then cat and then dog.
Okay. Help me actually type it. So you want me to just say the word lambda? I'll do it up here, actually.
Parentheses,
Okay, parenthesis, lambda.
and then parentheses, cat, parentheses, and then dog.
Close parentheses. Yeah,
Oh, yeah.
then dog, like that. Yep, so that would be a lambda calculus expression. And remember we said that lambda expressions are unnamed functions. So this guy doesn't have a name, but this guy takes one parameter named cat, and this is what it does. I heard it as it was coming out. Oh, yeah.
on YouTube.
All right. So, I heard it as I was saying it. Okay, so in any case, this would be the body of the function. This would be the parameter list of the function. Okay. Who said language theory couldn't be entertaining, right? All right. So, in any case, that's our second production. What about our third production? Give me an example of our third production. Don't overthink it. We have a list of stuff here, right? How many stuffs? 2 stuffs. Okay. Each of those stuffs is what, Evan? Beyonce, sorry. My apologies. Well, no, this is a list, correct? And this list has 2 elements. Here's element 1. Here's element 2. What kind of animal is element 1? What kind of element is element 1? One of these guys, right? What kind of element is element 2? One of these guys. So now give me an example of this production. Give me a string that matches that production. Dog what?
Dog.
Okay, in parentheses?
Yes.
All right. I'm getting very nervous with this group here. All right, so we have dog. Okay. Like that? Does that match the, is that our third production, fiance? Are you willing to stake your grade on it? So we had dog, we had Lippmann. Is dog this guy or one of these guys? It's an identifier, right? Is Lippmann this guy or this guy? It's an identifier. So this is a list containing two lambda calculus expressions, both of which are production 1, both identifiers. Make sense? All right. Similarly, couldn't we say dog is that a lambda calculus expression?
Use A, B as a list instead of expression.
Mm-hmm.
Or no, that'd be two identifiers.
So the whole thing's a list. First element is one of our productions. This happens to be production 3, right? Which is a list of lambda calculus expressions. Specifically, this is a list of two identifiers. So check mark there, we're okay. Here's the second element of that list, which fits production number 2, a list containing lambda, followed by open parenthesis, followed by a single identifier, Bob, followed by closing parenthesis, followed by a lambda calculus. Actually, was this identifier or lambda calculus expression? Oh, we're good. Lambda calculus expression. So, yep. So, followed by a lambda calculus expression. This guy's production 3. A parenthesis, followed by an identifier, followed by an identifier. Close parenthesis. Close parenthesis. Close parenthesis.
Like, can you go through those a little bit slower?
Well, why don't I write it? So we have, to start off, our opening and closing parentheses. We need to start with that. Okay? Then, this very first element here, this is production 3. So let's just mark it as P3 there. So production 3 says it's a list containing two lambda calculus expressions. In this case, the first lambda calculus expression is an identifier. The second lambda calculus expression is an identifier. Okay, so this matches production 3. Second guy matches production 2. Production 2 says we have a list containing the word lambda, followed by a list containing a single identifier, followed by a lambda calculus expression. Okay, which lambda calculus expression is this? This is production 3. So we can rewrite this. Let's copy this line here. This is production 3. This whole thing here is production 2. This is production 3. So we have a list containing production 3 and production 2, which contains a production 3. Okay? What time are we done in here?
Now.
Now. You want homework?
Yeah, we already do.
All right, I'll just make next time's homework harder. All right, questions about any of this stuff? Pretty easy?
So just go over that again. The cat does the dog.
Just to be clear. Like, all right, I'll make sure you do your Slack homework stuff, and I will see everybody on Thursday.